We were discussing the wave equation, which we derived in the last lecture. Tau square E by tau x square is equal to 1 by c square tau square E by tau t square. So we're relating again the spatial variation to the time variation or temporal variation. And we talked a lot about how space is not nothing. That if I place a positive charge here, for example, the electric field from this positive charge is disturbing the space around it, right? That space is not nothing, and this electric field or magnetic field exists in that space. Right, and the electric field itself or magnetic field itself is essentially carrying energy. Right, so these fields are the property of space because they exist in space, and they have some energy because if you have, for example, if you take a parallel plate capacitor, right? If you just take a parallel plate capacitor, you store, say, positive charge on one side and negative charge on another side. And this capacitor is a way to store energy, and that energy is coming from the electric field, right? So this electric field, even in a light wave, is carrying energy. So is the magnetic field, right? For example, the energy in an electric field is given by half epsilon naught E square. Similarly, the energy in a magnetic field is given by half mu naught B square. So in case of light, the energy that is in this electric and magnetic field is given by what we call as the Poynting vector, which is denoted by S. Excuse me. So here you not only have electric and magnetic fields that are varying spatially, but they're also propagating. So they're essentially they're representing transmission of energy, and because this energy is getting transmitted, you have a Poynting vector to denote that this energy, the transmission energy, is going along the propagation direction of light. That this light that's going in a particular direction is what is carrying this energy. So that's why you see a vector notation, right? And this Poynting vector S is defined as 1 over mu naught E cross B. This is a cross product because E and B are vectors. So and here, unlike other cases where, for example, when you study kinetic energy, you have no direction there. But here, the light is propagating in particular direction, right? So the energy is being transmitted along the direction. And so here we have a vector product to give us 1 over mu naught E cross B. So this gives us the Poynting vector, right? And so we can see that magnetic field can be roughly written as E over C. E over the speed of light is much weaker than the electric field. So if I were to use this here, you can see that the energy, the Poynting vector energy, would go like something of like E squared, right? Of course, over C, so because we are plugging in B as E over C. And from this energy, right, you can also get by dividing this total energy with say the area, right? For example, if I have a light beam that's focused into an area of A, right, I can take the total energy and divide it by this area, right, to get the intensity. That is the total power per unit area, right? And this total power, you can get it from the Poynting vector, which is 1 over mu naught E cross B, right? So now let's look at what would happen if we have two different waves, right? So let's say we have seen that we have the wave equation, right? And if we have two different electric fields, right? Let's say we have E1, which is, let's say, E01 times cosine, let's say kx minus omega t, right? K1x minus omega t, and E2, which is equal to E02. So this is the maximum that the electric field can achieve in each wave, K2x minus omega t, right? Same frequency, right? We're looking at we're basically looking at same frequency and also the same wave vector. So we're looking at same frequency and same wave vector. We're just looking at a slightly different maximum, E01 and E02. So if I were to add these two, the net electric field would simply be a vector sum of E1 plus E2. So I just do the vectorial addition, right? If these both are along the y-axis, I just simply add them up, right? Like a vector sum. So now when you look at the total energy, if you want to look at the intensity, the total intensity, remember, is proportional to what we saw is the Poynting vector, which was proportional to E squared, right? Because we saw that Poynting vector is 1 over mu naught E cross B, and if we look at B as E over C, we would get basically E squared over C. But the total intensity is proportional to this E squared term. So if I have two electric fields, right, E1 plus E2, if I want to look at the total intensity coming from this, right, if I want to look at sorry about that. If I want to, so we have the E net, the total electric field from two different fields, as a vector sum, right? E1 plus E2. So if I want to look at the total intensity from these two electric fields, I will have to square it, E1 plus E2 squared. So that would give me E1 squared plus E2 squared plus an extra term, 2 E1 dot E2. Right? So this extra term, right, because intensity goes as the square of the electric field, this extra term is what we say is the interference term. So it is because of this term that you see interference phenomena in light. That basically when this is for example, if I have E1 and E2 instead of plus, if I have a minus, right, then this is going to be negative here, right? So you could have, depending upon how you superimpose two different electric fields, you can have them cancel out or not cancel out, and that basically comes from this extra term, and that's what leads to either constructive or destructive interference. Unfortunately, to study interference further, we'll have to spend much more time. So that comes in optics part 2. So far we have been focusing on geometric optics, and in part 2 of optics, we could focus more on the wave nature and a little more into the quantum mechanics of materials and and where we basically could see how lasers come about and Einstein's equation, so on and so forth. But that is outside the scope of the first part of the optics course itself. But in any case, it is this extra term, this interference term, that leads to either constructive or destructive interference. Now we just discussed, we were just mentioning lasers. So when you see a laser pulse, for example, if I have a laser, right, and I get a pulse of light from this laser, this pulse of light is not just E cosine kx minus omega t, because E cosine kx minus omega t is basically, it can go, it's infinite. It doesn't have or sine, E cosine or sine, it doesn't matter which one, right? They both are basically infinite. There is no, they go to zero and they vary between -1 and +1, but they essentially, the wave does not die anywhere. It doesn't go to, it just is basically infinite. For any x value, right, you just have this oscillating wave. But in reality, the pulse that comes out, we have discussed this particular concept of wave packets even when we were discussing wave particle duality in the first 2 lectures. That when we say that when we look at a pulse of light, we are not just looking at one component of electric field, but you're looking at many different components of electric field that are superimposed on top of each other. So you don't have just basically one electric field there. So if I have, let's say, in a pulse, you can see how the pulse comes about. So if I have one electric field that goes as k1x minus omega 1t, and another electric field which has a different wavelength and a different frequency, right? If I do this, right, the net result of the electric field, the net electric field, would simply be E1 plus E2, right? Or I could write that as E0, right, cosine k1x minus omega t plus cosine k2x minus omega 2t. And here we could use a trigonometric identity, that is cosine A plus cosine B is equal to 2 cosine, right, A plus B by 2 multiplied by cosine A minus B by 2. So we have cosine A plus cosine B, and from this trigonometric identity I can convert that into 2 cosine A plus B by 2 times cosine A minus B by 2. So now I could write then the net electric field as 2 times E0, right, cosine k1 plus k2 by 2x minus omega 1 plus omega 2 by 2t, right? This is A plus B by 2, and then I have A minus B by 2, so I would have cosine k1 minus k2 by 2 x minus omega 1 minus omega 2. We're just simply adding up 2 waves that have different wavelengths and different frequencies. So on the previous slide, that's what we have, one particular wave with one wavelength and one frequency, the second wave with a different wavelength and a different frequency. And if I add them up, I just simply get cosine A plus cosine B, and from this simple trigonometric identity, I'm getting A plus B by 2 and A minus B by 2. So I'm adding up in x and in time, right? So I have to add up k1 and k2, then I get the first term. If I subtract k1 and k2, I get the second term. I have to do the same thing with omega 2, right? And that's what we did here. We added first and then we subtracted first. In between, it's always negative, right? In between, it's always negative, kx minus omega t, right? So that's why it's always negative. So now here, then I can write now a new way of writing this would be, if I could write this k1 plus k2 by 2 as a new k, let's call it kp. I'll tell you why we're calling it p, and we can write omega 1 plus omega 2 as omega p, right? Similarly, I can write k1 minus k2 by 2 as kg, and omega 1 minus omega 2 by 2 as omega g, right? So if I were to do that, then I can rewrite this net electric field. Instead of k1 plus k2 by 2, I would just write kp. And instead of this k1 minus k2 by 2, I could write just kg, because that's how we're defining them to be. Then I could write the net electric field as simply 2 E naught cosine kpx minus omega pt cosine kgx minus omega gt. And recall that kp is k1 plus k2 by 2, and omega p is omega 1 plus omega 2 by 2, and kg is the negative part, and omega g is similarly omega 1 minus omega 2. So this is essentially a superimposition of two different waves. In the first part, kp, you're adding both k1 and k2, and here you are subtracting, right? So the wavelength of this particular component would be very different from the wavelength of this. So if I were to plot this, suppose, let's say, if you take k1 to be 1 unit and k2 to be 2 units, right? Or let's do it the other way around for simplicity, 2 and 1, right? Then you would have k1 plus k2 by 2 would be 1.5. Whereas k1 minus k2 by 2 would be just half, right? So the wavelength here, right, k1 minus k2 is smaller than k1 plus k2, right? And this wave number k is inversely proportional to the wavelength, right? So if it is smaller here, you would have a longer wavelength. k1 minus k2 is a smaller number, so lambda, the wavelength, would be longer, right? So for this kg, you would have a longer wavelength, right? So I could draw this something like that. And for this kp, it's a larger number, so the wavelength is shorter, so it would be something like this, right? Shorter wavelength. So then you have a multiplication of these two factors. So the net wave is a multiplication of the dotted. This is coming from kg, this is coming from kp. Kp has shorter wavelength because k is greater when you add k1 and k2. And kg has a longer wavelength because you're subtracting k1 and k2, right? So then if I multiply these two, the resultant wave that I get would look like something like this, right? It would look like, right? So it would look like the larger wave superimposed on the smaller wave, right? Or essentially what you have is a pulse, or what you have in case of normal wave addition, what you call as beats, right? So what you get is beats. The first part of the wave, this part of the wave is superimposed on this part. So you have two waves, right, that are combined. So you essentially you're getting something like a wave packet, right? And we call this we call this particular wave, where we wrote kp, as the carrier wave, as the carrier wave, and this dotted kg as the envelope. So this kg, the envelope, is essentially embedding this carrier wave to make it look like a pulse. So what we would have is basically this is the carrier wave, right, which is embedded inside the envelope. So we have, this is the envelope, this dotted one is the envelope. So the envelope is the one that has omega g and kg, and this is the carrier wave, which is kp and omega p. So we have, when we add two different waves that have different wavelengths and different frequencies, what we are getting is beats, or we are getting something like wave packets, right, that can actually describe the pulses of light that come out of, say, a laser. So here, when we denote P and G, this P means the phase and G means the group, right? So we have two different types, the phase velocity and the group velocity. Okay, so the phase velocity and group velocity depend upon what kind of carrier wave you have and what kind of envelope you have in a pulse, right? So to understand this in a very physical way, imagine that there are several people running the marathon, right? There are several people running the marathon. So if I were to represent each person running the marathon as a dot, right, each person is running with their own velocity, right? Each person has their own velocity, but as a group they're moving together. The entire marathon runners are moving together, right? So I can get a group velocity by looking at the group of marathon runners moving as a whole, but inside each person has their own velocity. They have different velocities. It's a crude way to explain this, but it gives you a very nice physical picture to understand the difference between group velocity and the phase velocity. So in any pulse you have two different waves, right? At least two different waves. One is the carrier wave and another is the envelope. And the carrier wave gives you the phase velocity. Recall that Kp is what we looked at as K1 plus K2 by 2, and group velocity is Kg given by K2 by 2. So in general you have in a pulse not just two waves, but you have many waves, right? So to get the phase velocity in a group of waves, you can get the phase velocity, right, as Vp. And in general, light follows is a transverse wave, so it follows the equation that the velocity is equal to nu, the frequency, this is the frequency, times lambda, which is the wavelength, right? So, or you can write this as, you can multiply with 2 pi, right, and divide with 2 pi. So it remains the same. 2 pi times nu is omega, and lambda by 2 pi is 1 over k. So the phase velocity is given by omega over k. Whereas the group velocity, recall that we got kg by subtracting k1 minus k2 by 2, and omega g as omega 1 minus omega 2 by 2. So the group velocity, because you have this negative sign, right, it is the difference between omega 1 minus omega 2 and k1 minus k2. So it is delta omega by delta k. Whereas here you're summing it up in case of the phase. Here you have the difference, so that's the delta omega by delta k, or in general you can write it as d omega by dk. So this is the group velocity. once again, so you have, in a pulse, you cannot just have one cosine wave, because that does not diminish anywhere in space or time. So in real life, when we have light pulses, they're composed of many different waves. And what we have seen is an example of two waves mixing with each other, and using a simple trigonometric identity, we were able to decompose that into a carrier wave, which has a phase velocity, and an envelope, which has a group velocity. And just based on those definitions, we are basically deriving this phase velocity and a group velocity, right? So that is the difference between the phase velocity and the group velocity. Okay, so we'll stop here for this lecture. Thank you.